This is All Things Ansys, a podcast from the technical support staff at PADT. Episode 143, a look at GPUs for Ansys Fluent and news and events from the world of Ansys. Greetings, I'm Eric Miller, one of PADT's 3 owners and your host for these podcasts. It's been a few months since our last episode, I think 2. Our team's been super busy visiting customers and providing support, as has the Ansys ACE team, who we wanted to be part of this episode on GPU usage for Fluent. So we're lucky to have them join us today. So here we are in July, halfway through 2026. Of course, the most important part of the 6 months is the continued integration of Ansys products and staff in the Synopsys organization. From our perspective here at PADT, things are going really well, especially when we look at the development team and all the new features and new tools in 2026 R1, which was released in March. Our support team is now done with all the certification and training and testing. I don't know if you know this, but if you're an Ansys channel partner, we have to have someone certified in everything we sell, and sometimes multiple people. And it ain't easy. It's a really, really good process that they make us go through to not just learn it, but then test us on it. So we're all caught up on that, which is really, really cool to see. We also need to talk about AI. So if you're not aware, Synopsys is leaning in heavy with some very practical applications. There's a lot of press releases out there, and who doesn't do a press release that says AI? But what the Synopsys team, both Legacy Synopsys and Legacy Ansys, are doing is really finding ways to use it to make you guys more productive. So yeah, it's the Legacy Synopsys side, of course, which is chip design, has always relied heavily on AI usage, and they're doubling down on that. But over on the Ansys Legacy side, we now have Mesh Agent in Ansys Mechanical, Ansys Geom AI for rapid simulation-driven geometry modification, Ansys Engineering Copilot, which is initially in Medini, Model Center, and I think Rocky, and then also Ansys Sim AI, which has been around for a few releases, just continues to grow and improve with different options and different ways to run it. So we're not going to talk about those today, but keep your eye on it. That's what's a lot of what is going on everywhere in the world, including the Ansys world, is around AI. And so we'll find some time to dig into AI within that Synopsys Ansys world at some point this year. We're getting a good handle on it here at PADT for a lot of things we do outside of simulation, and we're dipping our toes into it for the simulation side of things. So hopefully we can get some experts from the Ansys side to come and talk to us about that coming up here as we learn it as well and share it with you. So one area that we do have a good handle on is using GPUs to drastically speed up various Ansys solvers. And of course, if you've been around for a while, you know that Ansys Fluent has always been at the forefront of using all sorts of parallel solver technologies, including GPUs. So the good news is that they are making this whole GPU thing even better in Fluent, delivering bigger models, being able to solve bigger models faster. And since the AI bubble is pushing GPU technology forward at a rapid rate, the hardware has been improving for GPUs insanely fast, and the Fluent developers are jumping in with both feet to make sure that happens. So let's talk to both PADT expert on that topic and someone from Ansys who took the time to educate us on where we are with Fluent and GPUs right now. I want to welcome everybody to a discussion today about a great topic that it comes up every once in a while because it's really important if you're doing CFD simulation, which is GPUs and the Fluent solver. So we're gonna dig into Fluent GPU in a second, but first I want you to meet our guests here. So John, why don't you go first and introduce yourself, what you do?
Yeah, thanks, Eric. Hi, everyone. My name is John Elias. I'm an application support engineer at PADT. I work specifically on fluids and CFD applications. I've been in the CFD application engineering space for about 9 years at this point, and so I'm looking forward to contributing to the conversation from that lens.
Great. And Frank?
Yes, hi, I'm Franklin Kelecy, and I am a principal application engineer at Synopsys, and prior to that, Ansys. I have over 30 years experience in computational fluid dynamics with specialties in turbo machinery, aeroacoustics, high-speed flows, hypersonics, and just general applications of turbulent flow and heat transfer.
Excellent.
Yep.
Well, a good place to start really is, I think everybody listening probably has an idea what a GPU is, but maybe it's more the hype, especially with their usage around AI right now. It's everywhere, or maybe your video game background. But let's start with that question of what is GPU, and then when it comes to solving CFD models, how does it fit into solving those CFD?
I'll go ahead and take that
Please.
question. So a GPU stands for graphics processing unit, and way back when they were developed in the early 2000s, and people were wanting to accelerate just computer animations and graphics for games.
Hmm.
They were designed to do certain computations associated with graphics very fast. And the way it does it is to use a lot of cores, like thousands of cores, tiny cores that do specialty mathematical operations. Then around the same time, someone got the idea that, well, maybe these can be harnessed for scientific computation and with my background, specifically computational fluid dynamics, but of
Right.
course there are many other physics that are being supported, along with artificial intelligence and similar kinds of things. But so the idea then is that we have this processor, which is designed for graphics, but has a lot of these thousands of these tiny cores that can be harnessed for scientific computation. And each of these cores can do certain operations like a floating point, single precision, floating point, double precision, integer, etc. And so an API was developed and supported by NVIDIA called CUDA. And CUDA is sort of the interface between the programmer, this person wanting to use it for something like computational fluid dynamics, and the GPU itself. So the GPU takes our traditional flow solver architecture, which was designed for CPUs, the central processing units that we've harnessed in parallel, which are very smart, much more higher end than a typical tiny core for a GPU. But we're taking that same technology now, getting massively parallel with within the GPU by harnessing all those little cores. Again, thousands of cores within these typical GPUs versus having, say, 50 or 100
Mhm.
CPUs to harness in parallel. So that's the major difference. We have one chip doing a lot of work with thousands of cores. That's what a GPU can do for us.
That's okay. Very cool. Thank you for that explanation. And that's one question I often have is it the same card or is a GPU I would buy, so for say my video game system, the same as a computational GPU, or do they have specific GPUs made for scientific computation?
I know, John, you were mentioning that you had done used GPUs for gaming, perhaps in
Mhm.
your
Oh,
past, and you
yes.
can comment on that. I do know that maybe you can speak to some of the smaller ones, but the GPUs do range in size and
Okay.
power. But the ones that are designed just for gaming can actually support CUDA and
Okay.
can support scientific computation. It's just smaller level. Maybe John, you can add some color to that.
Sure. Yeah, absolutely. I think it's the same of really saying fundamentally, whether it's a consumer GPU or a more powerful high-end GPU, they're all running the same computations.
Hmm.
Again, I
Hmm.
think it comes back to just saying, if you get what you pay for. If you get a
Hmm.
more
Gotcha.
powerful GPU, it's going to run faster. It might be more energy efficient, but at the end of the day, they're running through the same computations. You just potentially have, say, a lower specification on some of those consumer level GPUs
Hmm.
versus more high end, powerful GPUs.
Gotcha. Gotcha.
Yeah,
Okay.
maybe I can give you an example here.
Yeah.
So one of the ways we measure the computational power of the GPUs is through what's called streaming multiprocessors, or SMs. So a typical consumer low-end card like the RTX 8000 from NVIDIA would have 20 streaming multiprocessors per card, whereas their high-end H100 would have 132.
Okay.
So much faster or much more capable because we have more of these streaming multiprocessors. And streaming multiprocessors, by the way, is basically one group of these little cores that I
Okay.
was talking about earlier. So a streaming multiprocessor may have hundreds of cores under or under its supervision. Anyway, so more stream multiprocessors, the more computationally powerful it is, and also RAM. So each card has a certain amount of random access memory. Typical consumer card might have 4 or 8 gigabytes, whereas an H100 has 80, and maybe something more conventional like an NVIDIA L40 would have more like 40 to 50 gigabytes of RAM. And as we'll maybe talk about later, that has a direct impact on the kinds of problems we apply them to. So something with smaller RAM and a smaller number of streaming multiprocessors would be suitable for a CFD, but a smaller model. Right. But if you want to do a larger model, you'll need more RAM and more streaming multiprocessors.
Good. That was very useful. I can get my head around that a little bit more. So let's talk about Fluent itself, right? So the Fluent solver, or solvers, I guess is the right term. What is accelerated, GPU accelerated in Fluent right now?
My explanation to folks when they ask that question is that when we set out to develop the Fluent GPU Solver, it was almost kind of a clean sheet of paper in the sense that we were dealing with a new architecture. So no longer are we dealing with these fast, more capable CPUs and harnessing them in parallel. We've done that since early 2000s. Now we have a new architecture where we're dealing with CUDA and all these thousands of cores on the GPUs. So what we decided to do, instead of just accelerating, say, a linear equation solver, one of the things that mathematical operations we do all the time in CFD is solving large sets of linear equations. And so some people went the direction of just accelerating just that part of the computation. But we decided instead to make the entire CFD computation, all the calculations we do for the equations we're solving, everything's done on the GPU. We're basically handing the whole problem over to the GPU chip at once, and we then run the calculation there, and then bring the information back to a node, which is typically the nodes are CPU. So if we're talking about GPU computing, we have a CPU involved at the front end, at the head end, where we're reading in the files. We then transfer the problem the problem definition on the CPU to the GPU. It then runs it does its thing, and then sends the information back. That's what's different, is that we're when we to develop the GPU solver, we wanted to make sure that all the computation was done on the GPU, which makes it extremely fast. There's no overhead going back and forth between the CPU and the GPU side. So that's what makes it, in our case, up to 10 times, an order of magnitude faster than a typical CPU setup. And we always have to be careful here to make sure we know that when we're talking about speed, we're talking typically numbers of CPUs versus, say, one L40 card or one H100 card. So we always want to make sure we're comparing a hardware configuration to another. But given a typical kind of configuration that most of our Fluent users are using, something like maybe 100 CPU cores, we can use maybe one H100 card to get an equivalent actually much faster performance than those 100 cores. So again, people seeing 4 to 5 to 10 times faster than their traditional environment is not unexpected.
If I could,
please, John.
If I could add to this too, I think Frank gave a great explanation too of, say, how the GPU is able to accelerate the Fluent solvers. I can also add a little bit about, say, which solvers in Fluent are currently supported. And so that's also something to say, it's still being developed. And so there are some physics capabilities, some solver settings that are not yet supported by GPU. But I believe the vision is to have all of that ultimately supported. But there's already a lot of capability in terms of, say, which physics you want to include with GPU acceleration. Some of those could include physics such as standard incompressible flow, compressible flow, conjugate heat transfer, where you have, say, solids included for thermal modeling, some radiation models, chemical reactions, multi-phase flows. I'm giving this at the general level, and I'd encourage anyone listening to review the documentation, because the Fluent documentation has a really comprehensive list of which physics specifically are currently supported by GPU solving. Also, some that are limitations that exist today. And so that is, I believe that's going to be an evolving list as the versions come out in the future. And so I'd always encourage you to check what's available today, how that aligns with your specific needs as well.
That is really good input.
Right.
Yeah. Yeah. Um, so yeah, that's important because I've been doing this too long. So I remember when it was just they would just send the linear equations over to get solved. So we've moved that whole workflow over into the GPU. So that's really good to know. So that speeds things up quite a bit. So we talked a little bit about memory, and I think especially because memory is so expensive right now, we should talk a little bit about the memory architecture and how that affects performance. So these GPUs have memory on them, correct? And then there's your memory that's associated with your CPU and your whole system. So I don't know, Frank, if you can comment on that. What does that look like?
Okay, that's a great question. So what really is the driver here for the size of the model you can accommodate is the onboard RAM associated with the GPU card.
Okay.
So your CPU server may have a lot of RAM, and that will of course allow you to read in large files. You'll have to have a sufficient number of CPUs and RAM to read in the model size that you're interested in, and then you send that over to the GPU. Now, the GPU solver can take typically numbers like 2 to 5 gigabytes per million cells, depending on what models you're activating. So our rule of thumb is if you're using one of the lighter memory, in terms of memory, the lighter models like a segregated solver, single precision, you might only require 1 to 2 gigabytes of RAM per million cells. If you're using the coupled solver, which requires more memory to be allocated, and you're using double precision, then that will require maybe more like 5 or maybe a little bit more gigabytes of RAM per million cells. So you can use that as a way of judging how much onboard RAM do I need for my GPU. So typical GPUs now have 40 to 80 gigabytes. Some have more now. And so in many cases with one card, you can accommodate 10, 20, 30, even, and more million cells. Again, depending on how you which version of Fluent you're starting. Now, it also brings up another point, and that is single versus double precision, because on the GPU, that's determines not only the RAM consumption, but also speed too. So if the GPU solver has been tuned to run very nicely with single precision, and if you can run that way, you can run very, very fast, very large problems, things 100, 200 million cells very efficiently. Now, if you need the extra precision, maybe you're doing some physics that requires it, like combustion or maybe acoustics, you have that capability. It does slow you down, but it's allowable, and also takes a little bit more RAM. So all those things go into your decision as far as how many cards do I need and how much RAM do I need per card and so forth. But you're right though. You do need to have enough CPUs and RAM to load the problem. But none of the computation is done on the CPUs.
Okay. Okay.
Right.
Good. No, something we haven't really talked about that you mentioned was cards. So I assume that the Fluent solver is still parallel in that you can run it across multiple machines, and then each machine can have, of course, multiple CPU cores, and it can also have multiple GPUs per machine.
That is correct. Yes, you can run a full. This is again one of the unique features of the Fluent GPU solver is the ability to run across multiple GPUs and do so relatively efficiently. Again, that's going to be very hardware dependent, depends on how you've configured your system. But in general, we're used to running on, for example, in our company server in Canonsburg, we're used to running 4 L40s together on a single node, or we may have 2 H100s on a node. So users will go out and buy a similar system where they have a head node and then certain number of cards available on that node. And but yes, it's designed from the ground up to run on multiple
Mhm.
GPUs. And when you think about it, that's kind of it's interesting. It does have an analog with CPUs in the
Right.
sense that you have multiple cards like machines, but each of the machines has a massively parallel system, associated with the GPU chip. So it's yeah, it's quite interesting, and also allows us to do some enormous computations. And if I may, let
Yeah,
me digress here, or not really
please.
digress, but talk a little bit about something happened last year. It was
Hmm.
an announcement that we made on a record-breaking computation we did at the Frontier system at the supercomputer at the Oak Ridge National Lab. We ran a 2.2, get this, 2.2 billion cell
Wow.
model,
Wow.
and we used 1,024 GPUs. Or
Wow.
we scaled it to well, it
Hmm.
can be scaled to 20. Let me see how the actual number here. I have
Hmm.
it here. But yeah, so yeah, it was using 1,024 AMD GPUs. And again, we did a scaling simulation. He ran 128, 256, 512. So just to let you know that,
Hmm.
we're pushing the boundaries here
Yeah.
of how the GPU solver can be used, where, 1,024 GPUs in parallel can be assigned to this 2.2 billion cell problem. Now, not everyone has a Frontier computer in
Exactly.
on their desk, right? But
Mhm.
the way that hardware has been accelerating, maybe in 5, 10 years, everyone will
Yeah.
have the equivalent of that
Yeah.
on their desk. So, yeah.
That's a really good point, and we were kind of discussing it before we started the recording. Is there's been Ansys and Synopsys have been really working very, very hard to keep adding capability, adding physics, taking advantage of the various software tools that the card providers or the GPU providers are doing. But can you I think you talk a little bit about how GPUs themselves have gotten better, right? I mean, it's been a lot of improvements, and have we benefited from that?
And John, maybe you can
Yeah.
handle that
Sure.
one.
Yeah, I'm happy to. So I think maybe that gets a little bit more into say, how does a GPU execute the
Hmm.
simulation processes as
Hmm.
well? And I think that can kind of help explain this.
Good.
So fundamentally with a CFD model, whether it's CPU, GPU, there's a term called partitioning where you have to split your model into a certain number of domains. Say if you've got 100 cores, you'd split your domain into 100 partitions. If you had, say, 100 streaming multiprocessors or SMs on the
Hmm.
GPU, you would split it and partition it there as well. But say with GPUs, they lend themselves well to something called embarrassingly parallel processes. That's a term you can look up on the internet. And essentially, it's because each of those SMs on the GPU is even further broken up, as Frank was saying, into even sub-processors too. And so there's, say, tons of these processors on the GPU operating in
Hmm.
parallel. When you think of CPUs, it's a smaller number of those CPUs going in parallel. I kind of think of an analogy like cars on a highway, where say if each car is a equation you're trying to solve,
Hmm.
CPUs are, say, just a couple lanes on the highway with a very high speed limit, whereas a GPU is a super wide highway, maybe 100 lanes with a low speed limit.
Gotcha.
And so that's something we're saying, which of those is going to get, more cars through the highway per hour? And the reason why it's working here is, say, the GPU is getting more cars per hour. It's getting more equations per second getting solved, and it's enabled through improvements in the bandwidth and connection speed between each of those multiprocessors. And because that connection between partition processors is not a bottleneck, it's able to solve a ton of those equations in parallel very quickly. And that's where, say, the partitioning speed between the processors, the clock speed of the processors in a CPU can sometimes be slower overall, which is why we're seeing these performance improvements in the GPU. Does that
Mhm.
make sense?
It does. It does. And of course, they're spending a lot of time and money making those better with every
Yeah.
release of the
Yep.
technology. So,
Exactly.
Yeah. And what's kind of cool, I always love this, is that, there's a lot of people using Fluent and the Fluent Solver and IcePack, say, to design the cooling system for these GPUs, right? And both on the data center side of things and on the desktop side of things to make it more efficient. So to make our GPU usage even better. So that's kind of cool how that works.
Yeah,
Um, mhm,
on that same topic,
yeah,
let me interject here that
yeah.
John was talking about the lanes and how one
Mhm.
was high speed and the other was low speed. Well, low speed means low power as well.
True,
So
true.
the GPUs can actually consume less power
Okay.
because they have such a wide lane.
Mhm,
The bandwidth is much larger for the data versus the CPUs. Energy efficiency
mhm,
is also another reason people are turning to GPUs is because we can do essentially these supercomputer computations, but also consume much less energy. Plus the fact that the form factor,
yes.
you can purchase your own GPU cards and put them in a box, and it would actually fit on your desk, right? Is much different than having a lot of these CPU cards in a server in a
Mhm,
data center that has to be cooled and maintained and so forth. So I think people are finding that, yeah, not only is this a resource I can deploy more easily, but also consumes less energy
mhm,
and
mhm.
takes less effort to cool. So yeah.
And we should also mention, in case other folks are listening, that the rest of the Synopsys product line, the legacy Ansys as well as legacy Synopsys tools, are heavily used by the GPU, especially NVIDIA, to design the chips
Hmm.
themselves, the packaging. So it's the advances that we're taking advantage of in the GPUs are very much driven by simulation technology. So I
Right.
just love that. Yeah, it's really cool.
Yeah.
Um, so let's talk a little bit about mistakes. So you both work with customers out there. I'm sure you deal with customers all the time that are going out and buying a machine or trying to run on a machine that's got GPUs on it. What's I'll start with you, John. What's the most common mistakes that we can let people know so they can avoid them?
Yeah, absolutely. It's a great point. So, two of which that I think of today, well, even three potentially.
Mhm,
So, I'll go through each. First of all, it's understanding the compatibility of the GPU solver with what physics you're trying to include.
mhm,
So,
mhm,
just fundamentally making sure that today, in the latest release of the software, what you want in your physics can actually be solved with the GPU libraries. Again, like I said, that's evolving. I'm not a product manager, so I can't
mhm.
really say what and when is coming in the future, but I know it's being built for the future. And so, first of all, making sure that your physics you want are going to be compatible. The last thing we want is for you to buy a GPU and then
Mhm,
you can't
mhm.
run the
You can't run
software.
it.
So that's number one. Another of which is understanding licensing implications.
Mhm,
So that's
mhm,
something too where for anyone using Fluent, you might be familiar with the term HPC pack. And that's something where if you purchase HPC packs, there's other possible licensing as well. You get access to unlock more compute cores for your simulation. There's also an analogous specification for GPUs when we're talking about those streaming multiprocessors or SMs. The more SMs your GPU has, you may need to purchase additional licensing to enable that too. So that's another thing as part of budgeting. You want to make sure to include that, or maybe get one that just works with the default Fluent license. That's also possible. So that's another one. And let's see, what was my third thing? Oh, yes. Also, you want to make sure when you're evaluating if GPUs are a good investment for you, you also need to understand your baseline CPU system. You
Right.
know, if you've got 1,000 CPUs and you're trying to improve it by purchasing one GPU, that's something where you may not see a benefit. But then
Mhm,
again, if you've got a 32 CPU laptop, maybe one GPU is going to be a big improvement. So it's also understanding, making sure that you have the correct comparison in mind when you're looking at the future ROI of GPUs. There's a lot of opportunities where it could be better, but sometimes you just need to double check to make
mhm.
sure for your specific needs that it truly is going to be an improvement.
Frank, do you have any
Yeah.
experiences to share?
Yeah, so first of all, as far as ROI is concerned,
Mhm.
Synopsys has a GPU ROI
Good.
estimator online. There's a link that we could probably provide folks, but you could probably do just a Google search and find
Mhm,
it. But GPU ROI estimator, which will ask some pointed questions about, what do you need to do, and what size machine would you like, et cetera. And it'll come up with some suggestions and also estimate, what kind of return on investment you would get from using the GPU versus a traditional CPU system. And one thing I also wanted to point out as far as CPUs versus GPUs and the Fluent solver is that the Fluent files are fully compatible between the two solvers. So I can take a GPU solution and read it right into the CPU solver. For example, let's say there's some physics that's not supported by the GPU solver. I can read it in the CPU solver. Paste and data files are there, all your solutions there. I can activate some multi-phase model that's only supported by the CPU. So you can go back and forth between the two sides if you so desire. So we do have the ROI estimator, and also as far as the size of cards you need and number of cards, usually you're going to have to do that as a package, right? So there's going to be a head node, CPUs, there's going to be the number of GPU cards you want on that, and it's all going to be bundled together as a system. So the main thing is to determine from the RAM specifications for the card, how much RAM you're going to need, what size model do you want to do, up to how many million cells, and then we can help you estimate, what size cards plural that you'll need. And again, the more streaming multiprocessors, the faster it will be, and more capable your system will be, and the faster your turnaround, and the larger the model you'll be able to do.
Larger models. Yeah, I'm glad you pointed that out. It's sometimes it's not the speed, it's the size that we're going for some of the simulations. Yeah,
exactly.
Eric, if I could add a little bit too on the ROI topic here, sometimes I think too about, say, what questions can a customer ask themselves to say, is moving to GPU worth the investment? And sometimes the way I think about this is you can ask a couple questions about, are you satisfied today with things like your current simulation turnaround time, your current simulation physics complexity, your current simulation accuracy, and even your current electricity bill. And if you're not satisfied with any of those, and GPU is found as an option to accelerate your turnaround time, say adding physics complexity, adding accuracy, that takes more turnaround time as well. And so by accelerating through GPU, you can get those results in the time frame that you need them. And of course, save on your electricity bill, like Frank was saying too. So all of those questions are things that a customer can ask themselves outside of purely the purchase of the GPU to say, is it really worth it? Or am I happy with accuracy, physics inclusion, turnaround time? If you're happy with all of that, you might be pursuing acceleration that doesn't make sense.
Yeah, it's a significant investment, so you need to make sure you know what that ROI is going to be. Yeah, good point. Okay. We kind of talked about a lot of the stuff we wanted to move into futures and then some suggestions. But so I know we can't always talk about what's planned and on the roadmap, but at least what we can, Frank, what are the wizards that spread across the Ansys and Synopsys world working on for GPUs and Fluent?
Yeah, that's a great question. And I do know that they continue to advance the state of the art of computational fluid dynamics within the GPU architecture. So for example, we're coming out with a full suite of turbomachinery models. There's going to be advances in boundary conditions for things like acoustics and combustion. More multi-phase models, of course, will be put there, because one of our legacies with the Fluent code has been our rich multi-phase modeling capability. And then coupling too with meshing and geometry. One of the things that we're working on now is something called Fluids One, which will have an entire workflow available to you. It's going to have kind of if you're familiar with the Ansys Discovery environment, it's going to have that look and feel. There's also a web UI. So we have a web interface that's been around for a little while. That's also hooked into, you can use the GPU solver that way, where you can be running your GPU solution on a server and then link to it from a web browser, of your choice, and then run it run the model, stop it, do some post-processing. Very innovative and very interactive environment. So that's kind of what's, the things that we're working on. Again, we're working on just essentially making the GPU solver equivalent in every way to the CPU solver and beyond, to go even further beyond in terms of performance and new models and innovative ways to couple not only CFD with traditional, say, mechanical modeling, but also beyond with other physics as well. So, so be on the lookout for all of that as we move forward.
They are keeping busy out there.
Absolutely, that's right.
So I think we kind of covered it, the next question, which is, what should teams do, team evaluating GPU acceleration do? I think we kind of covered that. You need to do the ROI. You need to understand what size your problems are, what physics you're dealing with, all those things. I don't know, what advice besides that would you give somebody that's like, okay, we're doing some pretty high-end stuff. We're sitting around waiting a long time. Our problems don't run on the equipment we have. We're going to invest in a GPU system. What should they look at besides that ROI calc, and what kind of problems they need to solve?
Well, if I can take that question. So, what else do they need to look at there? Would be, if you're wanting to do specific physics that, let's say that you want to do, again, some specific physics that aren't necessarily supported natively within the GPU solver, one thing that you might think about is that the GPU solver does allow for what are called user-defined functions. So people using Fluent remember or have used the user-defined function, which you write code in C. But guess what? This interface, and a lot of the interfaces, by the way, within the Fluent architecture are moving towards Python. We have Pythonic interfaces. So you can write a Python code and connect it right to the GPU solver. So there may be some innovative ways you can make use of that to go, beyond, what you're maybe considering as far as the physics are concerned. If you have maybe ways you'd like to customize, and also in terms of customization, there's a lot you can do with Python. We have PyFluent. And PyAnsys. So you can write interfaces from Python to innovatively communicate with the CFD solver, do a lot of automation, customization, and just just really the sky's the limit there. So wanted to get that plug in for PyFluent because people wondering, well, I want to be able to do this, this, and this. Well, you can do it. You can program it, or you can get us to help you with programming it. And the way AI is going now, AI can probably help you program it, right? So all right,
definitely. Yeah, it's a good point, because I think sometimes if you're a long-time user, you tend to use the code the way you've used it for a while, and we forget to look at these new things. And definitely the open customization capability and user programmable functions being available and the GPUs is really great news. So I don't know, John, what advice would you give, besides if you're an Ansys or you're a PADT Ansys customer, and contact PADT and we'll help you figure out what you need. What else would you like to pass along?
Exactly. Yeah. So first of all, that's the big thing, is reach out for help, and we'd be happy to assist you further. On the other side, I'd say really at the end of the day, the physics haven't changed. We're still solving the same physics here. A flow solution is a flow solution with these fundamental equations that we're solving. So when it comes down to it, it's really how are we solving that solution between CPU and GPU? And so fundamentally, you'll get a very similar result. Of course, there might be some nuances of different, you're not going to get a line-on-line solution possibly just because of different compute hardware. But the results, you're solving the same thing here. And so really it does come down to saying, what are the benefits of GPU here that would serve you? And understanding, are those benefits worth the investment to you? Making sure that the current physics solvers are compatible with GPU. But really it is that of just saying you're solving the same model here. It's just a new way to solve it that is accelerated in many cases.
Many cases.
So that's the way that I see it.
Awesome. That's great.
All right.
All right. Well, we could talk about this a lot more, but I think we'll wrap it up there. We'll have some resources available as well in the notes, hopefully. And but I think the main thing is just contact your support provider, right? And before you make this investment, and make sure you understand all the ins and outs of it and how it can work. And it's a good investment. I know that we use it here on the consulting side of things, and I know that many of our customers are, especially some of the larger customers, are very happy with these capabilities. So. It's a nice enhancement over the years that keeps getting better and better. So,
Hey, Eric,
John, Frank, yeah, one more thing. Frank, you want to add something?
Yeah, I want to make a quick plug for
Please,
those out
please
there
do.
who haven't had their question answered,
Yes.
which I'm sure are many.
Mhm.
I want to make a plug for the Ansys innovation space, and there is an Ansys Fluent GPU Solver FAQ. So you can probably put that into your search engine,
Good.
and it'll come up with the web page. There's basically an FAQ on things like which license is required to run Fluent on GPUs, where can I learn more about HPC licensing, and so forth. There's a whole list of questions and answers there. So just direct your browser over there, and hopefully that'll answer a lot of the questions we weren't able to get to today. But thank you.
That. That's great.
Yeah.
Thanks for bringing that up. That's great. Well,
Yep.
Frank, John, I really appreciate this discussion for updating us and our listeners on what's new with Fluent GPUs and our GPU usage with Fluent. And we'll have to, I'm sure we'll get a couple more generations of hardware coming and some more enhancements of the software. So maybe in a couple of years, we can come back and take a look at this again and see where it's at. So see how it's improved. So really appreciate it.
Yeah, no
Absolutely.
worries. Thanks. Appreciate
Yeah, it
it.
was a pleasure,
Yep.
Eric. Thank you.
Yep. Take care.
Okay, that was really good, guys.
Okay.
Appreciate
Thank
it.
you, Eric.
Yeah,
Yep.
yeah. I'll probably edit it over the weekend. I might not. We'll see how busy I am doing other things, but Trevor will reach out when it's ready to go. So
Sounds good. Yeah, send me the link. I can
Will do.
can distribute it within Ansys. Also, real quick, I was talking with Teresa Thompson. Yeah, so our marketing
Yes.
connection, yeah, here, and she would like to maybe collaborate with you guys
I'd love to do it.
on these podcasts because again we're doing the webinar series and yeah, Teresa Duncan, sorry, yeah, so Teresa Duncan. I just gave her Claire's contact info, but if you're a better contact, maybe I can give you your info, Eric, or
let's start there and see where it goes, because we would love to do that. I know that we had talked about it a little bit before the merger, and now that the marketing team is coalesced into its new configuration,
yeah,
it's probably a good time to have another conversation. So
yeah, because I think all of these things can kind of go together. This is a great topic for right now because there's a lot of information that we just put out on the GPU solver that we can share with folks. So
yeah,
all right, thank you.
I love it. Thanks, guys.
Yeah.
Talk soon.
All right, take care, Eric.
Bye.
Okay, bye-bye.
As usual, we just scratched the surface on that topic, but as you heard, if you are solving in Fluent, you need to do some homework to see if investing in a newer GPU or the ones you already have will deliver an ROI for you. I know it does for us, and many of our customers have found a huge benefit from that investment. The one thing to point out is that there's an article out there on the Ansys blog. It's 3-parter actually, called "Unleashing the Full Power of GPUs for Ansys Fluent." It's a little bit old, 2022 through 2025, I think, the 3 different parts. But do check it out. There's some good background in there. And then with this podcast, it kind of brings you up to date on everything. Also of note is the Fluent GPU Solver Hardware Buying Guide, and it's in the innovation space. And I found it, as mentioned in the podcast, by just searching for Fluent GPU Solver Buying Guide, or I think I just did Fluent GPU Buying Guide. But I found it. Check it out. There's some really useful information in there. That's a good starting point. But the best thing for you to do is reach out to your support provider and ask for questions. As we said, because of memory prices, this is not a no-brainer investment like it was. But if you run larger models that take a long time to solve, it can be an investment that pays for itself pretty fast. So check it out. All right, and that leads us right to our commercial. And for this episode, I want to go back and cover PADT as a whole. We haven't done that in a while. So if you didn't know, PADT is an 85-person company based in Tempe, Arizona, with offices across the Southwest that is the leading provider of products and services to companies that design and manufacture products. We started the company back in 1994, so we just celebrated our 32nd anniversary. Back then, we took 3 core computer-aided engineering technologies that we were using at what was then called Allied Signal Engines and is now Honeywell Aerospace, and built a consulting company around them: simulation, advanced design, and 3D printing. a few years in, the vendors who were providing us with these tools asked us to become resellers. And that's how we became an Ansys channel partner and started selling Stratasys equipment as well. And over the years, we sold a lot of different stuff. One of our more successful non-Ansys, non-Stratasys add-ons is a product called Flownex, which we talked about in a previous recent podcast. It's a 1D thermal fluid solid tool. We used to sell metal 3D printers for EOS. We kind of still do that, but not so much. We also sold scanners for a while. What's new for us from a reseller standpoint is we've added this very large 3D printer technology called Rapid Fusion. So think of it as a 3D printer on the end of a robot arm. We can print whatever your robot arm can handle. So it's a pretty cool technology. It's got me choked up. I'm so excited about it. We continue to provide services as well with teams dedicated to product development, simulation, and 3D printing as a service. You can learn more about us at www.padtinc.com. Most of you know us for Ansys, but we do much more. So please recommend us to people you work with or consider reaching out for your own simulation, software, or product design needs. We're here to help with both sales and consulting. So thanks. All right. Let's jump over to the news side of things. And we always start with stock, which is now Synopsys stock. So what I'm seeing is kind of a slow drop since our last podcast when we talked at the beginning of May. It got a little bit after that last podcast. It got to a really nice peak. It was kind of close to where it was in January at 534. That was in May, kind of end of May. I think it was the 21st of May. But now it's down to 337. So that's quite a bit of a drop there when the market closed before the 4th of July holiday on July 2nd. So what I'm having to get used to is that with Ansys, the price is driven by a lot of different factors, and a lot of it had to do with just the Ansys numbers. But Synopsys revenue is so heavily tied to semiconductor that it can go up and down a lot because of something that has nothing to do with them, right? So still trying to get my head around that. And again, I'm not a stock guy, and so I'm fumbling a little bit. But I thought, well, why don't I take a look at what semiconductor stocks are doing? So there's an index called SOX. It's some long name, but it's basically semiconductor stocks. And I'll be honest, where Synopsys has been flat for the year, that trend, that SOX kind of consolidated look at semiconductors is up 75% year to date. So the industry as a whole is doing well. Again, we talked about in the last podcast and maybe one before that. Synopsys has a lot of debt and they're making good sales, but I guess not enough for the Wall Street guys. So, although I looked around, I said, what's going on with Synopsys stock? And I found this article from a couple days ago that said it's undervalued by 23%, according to all these things that I didn't understand. So I don't know. It seems like people are saying it's a good buy right now, but then other people are saying hold. So we'll see. But let's take a look at news. And so that has, of course, moved from the Ansys website, where they used to keep it, to press releases on the Synopsys website. Most of them deal with chip stuff, so I won't cover those. But the one thing is some big news that's chip and Ansys related is that part of the synergy of the merger, the acquisition, is they are now releasing these things called multiphysics fusion solutions. That's a tongue twister, multiphysics fusion solutions. The basic idea there is that they've always had an integration between Ansys and Synopsys, kind of chip level tools. Now those are becoming really solid and strong. So they're calling them multiphysics fusion, and it's allowing engineers designing semiconductors to kind of do both. So these are the legacy products from each company connected together. That was in June, so it's really worth a read if you want to know what's going on in that space. So also since our last podcast, kind of their big press releases, they did a second quarter financial report. And I still, haven't got my head on, is this good? Is this bad? I don't really know. There's such big numbers than what Ansys had. So speaking of big numbers, their quarterly revenue was $2.276 billion. And that was above what they expected, their prior guidance, they say. So the quarterly earnings, according to standard accounting practice per share, are 9 cents. And the non-standard, the non-GAAP EPS is 3.35. So they have raised expectations for full year total revenue to $9.6 billion. And it's driven by strong performance across the business. And they had there's this bookkeeping thing they're doing about how they book Ansys channel related accounting. People like us. And I don't really understand it, and they don't really go into it, but they're amortizing stuff instead of, I don't know. I don't really understand it, but they say that's going to cause some positive things to happen. They also sold or closed their processor IP solution business. That wasn't growing, so they closed that down. So there's some cost associated with that. So their summary also says that raising full year non-GAAP EPS guidance to $14.76. So that's a big jump from $3 at the midpoint on expand. This is the midpoint of their fiscal year, right? So end of Q2, expanding operating margin driven by strong cost discipline and accelerated synergies. So if you don't know, they've had some layoffs. They've definitely reduced their staff and they've consolidated. I know some of the people I know that worked in what used to be Ansys have now been kind of moved in with the teammates at Synopsys. So this synergy stuff is happening. It's really good. So I scrolled down and looked at some of the other numbers. So revenue is up from last year. It's $1.6 billion. And that's a good thing. On the gross margins, that's up $400 million. And then expenses are also up to $600 million. So income is down to just $17 million instead of the $345 million they saw last year. So all these expenses of the acquisition are really killing their bottom line. I like to take a look at cash and debt. So this is another thing to pay attention to. They have $2.4 billion in cash, which is down from $2.8 in October of last year. And guess what? Their long-term debt is $10 billion. That's down from $13 billion. So let's see here. They didn't spend all that cash on paying down that debt. There was only $300,000, $300 million, not $3 billion. So anyway, I can do math in my head. But anyway, the good news is their long-term debt is down from that $13 billion to $10 billion over the last 6 months. So we'll keep our eye on that as well. It's on their news site. Take a look if you're interested. Read what the analysts say. Put it into your favorite AI tool to see what it tells you it's doing. I love that the debt is coming down. That's a good thing. One thing that I noticed is that they did break out their interest payment for the last quarter, first half of the year, their fiscal year. They spent $296 million on interest to pay down that debt or to service that debt. So that's a big chunk of money. So hopefully they'll keep paying that down. All right, PADT news. We got nothing. No press releases from us. We got a low profile. Next part we always like to talk about if you're new to the podcast is I like to pick 3 blog posts that I read on the Ansys blog website that I liked. And the 3 I liked were one, which kind of fits into what we've been talking about today, scaling optical simulation with AI, cloud, and GPU acceleration. And that fits nicely into this discussion we had. It is optical simulation, but the one thing that it covers is also how AI and cloud are fitting into that. So it's a good bellwether for how other Synopsys-related products are going to be adopting these 3 major, what we call megatrends, and how that's impacting simulation. So worth a read, even if you're not an optics engineer. Another merger synergy event was how the Synopsys Simpleware product is being used with Ansys in silico medical simulation. So if you don't know Simpleware, it takes medical images like CT scans and X-rays and things like that. Those are basically layers within a solid. And then it turns them into, the user turns those into 3D models, solid models that we can use to mesh or do CAD with or whatever. So always a great tool, always there. We've used it over the years. We've used some competitive products, but now that it's part of the Ansys family, we're super excited because in the medical space, this is really important. If you want to model a particular organic shape of a heart or a lung or a kidney, you had a couple of choices that weren't, what's now Synopsys products. So they didn't necessarily work so well from a simulation standpoint. Simpleware gets simulation because it's part of Synopsys. So we're really excited about this. And the article, I went all that because I've been doing this for 30 years trying to get CT data into simulation models. So it's so cool to see this. Why I talk so much about it. Anyway, the article is called From Scan to Simulation, Advancing Medical Innovation in a Single Workflow, which is exactly what we all want. Single workflows for the win. Yes. So also, if you're a longtime listener, I love when we use simulation outside of what we usually use it for, and we apply it to sports. I just think that's cool. And so there's a really cool new article called The Devil's in the Details, The Science Behind Cycling it's a great look at simulation and cycling and the science behind cycling. So check that one out. On the PADT blog side of things, let me bring that up and tell you what we got there. We've got an article from Cynthia called Come Explore the New Granta Material Picker. And this is for optics. So, it's using Granta Material Picker in the optics platform. So you can now get access to things there. Also, I wrote an article since our last podcast called 40 Years as an Ansys User. So yeah, I guess you should have led with that. It's kind of a big deal. On June 15th of, I guess it's date right, 1986, some of you may not have been alive then, I showed up to work at what was then Garrett Turbine Engines. It became Allied Signal, is now Honeywell Aerospace. And after all the HR stuff I did in the morning, they sat me down with a manual in front of this VT100 terminal and said, learn this product. It's called Ansys. It's a simulation tool. I had no idea what they were talking about. And it changed my life, not just from a professional standpoint, but from finding something I really love to do my whole career. And most importantly, the great friends that I've made. Something a little almost choking up a little bit here for real. So I posted this article on LinkedIn, and dozens of people from the Ansys world that I've known, many for 30 years, chimed in and talked about how nice it was to be part of that whole thing. And it was really kind of meaningful. So yeah, 40 years I've been an Ansys user. Kind of crazy. So read my blog post on that. It's kind of cool. The other thing that we put out there, we've got two articles that might be interesting to you that are in 3D printing. One compares the FDM printer from Stratasys, the F900, which is their big boy, and the new F3300, which is kind of a faster, more capable large 3D printer. So check that out. That's from Pam Waterman. And then also she did a thing called Fast Fixtures with Fixture Mate inside Stratasys GrabCAD 3D Print. We've got since our last podcast, we also put out there an article about FlowNext 2026 R1. And then Josh did a really useful article. It's actually getting a lot of hits. I was looking at that, called Ansys LMU Util and Releasing Stuck Licenses. So I don't know if you know that sometimes you can get your license stuck. And it's he basically goes through step by step how you use the LMU tool to kind of free up that license so you can use it again. So that's a good one to check out. And what else do we have? Going to the next page. That was it since the last since the last podcast. So that is it on that end of things. And I'm going to switch over and take a look at our events page. By the way, you can see all those blog posts on padtinc.com/blog, and you can see all of our events on padtinc.com/events. Big thing for us, if you're here in Arizona, please join us for the Aerospace Summit, the Arizona Aerospace Summit in Tucson on July 15th. We will have a booth. I'll be doing a panel. There will be all sorts of people talking about, we'll have 3 separate tracks, one on aircraft, basically, although I think we call it air mobility or something like that to kind of include anything that flies through the air, one on space, and then one on defense. And we'll be getting together 3 times during the day as well as a group to kind of go over what we talked about in each session as everybody together, because of course the world of aerospace overlaps between those 3 segments quite heavily. And of course, simulation is an important part of that. So I will be talking about that quite a bit while I'm there. Just to let you know, in case we don't get another podcast out soon, also, I will be at the 2026 CEO Leadership Retreat and Golf Tournament, although I will not be golfing. And that's August 10th through 11th in Prescott, Arizona. That's a Tech Council thing. And we will be in August at SmallSat. We'll just be attending. We won't have a booth, but you look for people in PADT shirts. Thank gosh they moved that down to Salt Lake City with a big enough convention center. That was a great conference. Always been a great conference, but it was a little crowded when it was in a small town. Also in August, we will be at the Nuclear Energy Conference and Expo at the Hilton Anatole, I guess, in Dallas. We'll be attending there. So do look for, again, people in PADT shirts there. And we will be at the Turbine Engine Technology Summit the next week, August 31st to September 3rd. And that's at the Dayton Convention Center. So that takes us up through August. In September, we'll be at IMTS doing some manufacturing stuff. And also, we officially announced the date for Nerdtoberfest 2026. If you're from Arizona, you know that Nerdtoberfest is our big event every year. It's a big open house. We had almost 700 people, maybe a little bit more, show up last year. We want to have even more come this year. We basically turn our parking lot into a celebration of engineering and manufacturing. Everybody's welcome. Again, that's October 28th. And it's going to be from 4 to 8 here at our offices in Tempe. So I wanted to get that out there. You can register now if you go to padtinc.com/Nerdtoberfest and click on the right buttons. You will get to the registration page. So that is all of that for events. A lot going on over the next couple months. Busy time. Yeah, that's pretty much it. So I want to thank you for joining us for another episode of All Things Ansys. Don't forget to subscribe to our newsletter at padtinc.com/opt-in so you can keep up to date on everything we're doing here at PADT. One thing that we've added since probably the last 4 or 5 months is a lot of, I say we're out visiting customers. Well, we actually are. And we started sharing pictures. So it's a lot of cool pictures, just little snapshots of our employees traveling all over the world. We had a guy at a conference with the Ansys team around MBSE at an event in Tokyo, I think it was. It was in Japan. And so some cool pictures from that. So we're all over the place. Check out our newsletter. Again, that's /opt-in on the website. Also, don't forget to subscribe to this podcast. It really helps us get seen and spread the word and let other people know that they should just listen in. And as always, never hesitate to reach out. Thank you for joining us for the All Things Ansys podcast, episode 143. As a reminder, this podcast is not affiliated in any way with Synopsys. The opinions expressed are those of the people on the show only and not of their current or former employer. For more information, visit www.padtinc.com/blog, and please share your thoughts and questions through an email to podcast@padtinc.com. See you next time.